Okay, so let's look at what's going on here. We've got a table of values, and it says the table to the left shows the year and population. The population is in millions of Texas using an exponential model. Write an equation for the curve of best fit, then estimate the population of Texas in 2020. So we've got two things to do. We've got to come up with a model, and then we've got to use that model to estimate the population. So let's put our data into our table, but first of all, let me just show you something that makes things a little bit easier. Instead of typing in 1900, 1920, 1940, let's say, and usually they'll tell you to do this in a problem, they'll say let 1900 be t equals 0. So we would have 0 for 1900, 20 for 1920, 40 for 1940, 60, and 80. Okay, so that's what we're going to put into our table here. Go to Stat and Edit. It's the very first option. Okay, so 0, 20, 40, 60, 80. And then in L2, we're going to put those populations: 3.1, 4.6, 6.4, 9.5, and 14.2. Okay, so we've got to quit. So second mode, we've got to go back to our just blank home screen. They want the exponential model. So we're going to go back to Stat, over to Calc. Now you're used to using number 4, LinReg. That's for linear, but this isn't linear. This is exponential. So option 0 is exponential regression. So 0, scroll down to 0 or type in 0, is exponential regression, and then press enter. So our model is, and we're going to use P of t for population at time t. Now I'm just going to copy down what the calculator says first. It says a times b to the x. That's the general model, so let's plug in the specifics. A is 3.095. I usually round to 3 numbers after the decimal. B is 1.019 to the x. So there's our or not x, t. T. We're talking about time. T. Use a t as your exponent. Okay, so there's our model. It wants us to estimate the population in 2020. So do I plug 2020 in for t? Do I plug in 2020 for t? No, I don't plug in that exact number. Why not? Because I changed my t's. 1900 was 0, so if 1900 was 0, what is 2020 going to be? 120, right? Subtract. 220 minus 1900, 120. It's been 120 years since 1920, in the year 2020. Whole bunch of 20s, right? Okay, so we're going to plug in 120 in for t. And we're going to find our population. Okay, so according to this model, the population of Texas will be approximately 29.6 million people. I just rounded the way that the table was rounded. The table was rounded to the nearest tenth, so I just went with that. Okay, so 29.6 million people in 2020 is what this model predicts. Okay, so look at number 2. It says the table on the left shows the closing prices for the NASDAQ stock index at the end of February during certain years. Using an exponential model, write an equation for the curve of best fit, then estimate the year the closing price will reach $10,000. All right, so let's do the same thing that we did before. We're going to let 1992, the first year, be t equals, or you know what, actually, hang on. Let's do t equals 2. Okay, we'll say 1990 was 0, so 2, 4, 6, 8, 10 is what we will put in list 1. Now, if you want to clear out what is in list 1 and list 2, do not press delete. Move your arrow up to the L2 and the L1 and press clear and press enter. If you press delete, then it'll make the L1 and the L2 disappear. And we really don't want that to happen. So 2, 4, 6, 8, 10. L2, 633, 793, 1100, 1771, and 4,696. Okay, so quit. We're doing the same thing, so I'm just going to press second enter, or you can go stat calc 0. Okay, get our regression here. So we'll stick with P since we're talking about price. So P of T is 320.276 times 1.272 to the T. So that's our model. Let's look at the question. It says, estimate the year the closing price will reach $10,000. So it doesn't give us a time to plug in, it's asking for the year. So anybody have any ideas of what we should do here? Any thoughts of what we should do to figure out how to figure out T when the closing price will reach 10,000? So tell me this, what part of the equation should the 10,000 go in for? Does it go in for T or does it go in for P of T? Is it a time? Okay. It goes in for P of T because it's a price. P stands for the price. So our equation is equal to 10,000. We are looking for estimate the year. We are looking for the T. So what can we do to solve that equation? We were just practicing it yesterday. What if you don't remember how to solve an equation? What can you always do to solve an equation? I don't have any answer choices, so I can't plug them in. But how can we always solve an equation? Graphing? How can we solve equations by graphing? You can. You can. We can always solve an equation by graphing. Here's what we do. We plug the left side into y1, so 10,000. We plug the right side into y2. And then I'm going to graph it. And I can't see anything. Anybody have any ideas why I can't see anything? Oh yeah, it's way outside my window because I put 10,000 in there. My normal window is negative 10 to 10. So we got to change the window. Okay, we've got to change our window here. Our x values are correlating to our years. Okay, our x values are correlating to our years. So we don't need negative time. That doesn't make any sense. So I'm going to make my x minimum 0. I have up to year 10 in my table. Obviously, I got to go past that, right? Because I'm only up to less than $5,000 at year 10. I got to get to 10,000. So how about we make it 20? just be on the safe side. Okay, let's talk about the Y values. The Y values refer to closing price. Our minimum closing price was 633, so I'm going to go to like 500. Okay, and we need to get up to 10,000, so I'm going to give myself a little bit of a buffer here. I'm going to go to 10,250 just so that I can see. I don't want it to be right there at 10,000 or it's going to cut off my line. So now I'm going to press graph. There's my 10,000 right there. Here comes my exponential function. Now, what about that's going to give me the answer? Y'all know this. When you have two graphs, when you have two functions on a graph, how do you find where they equal each other? Where they cross, okay? The intersection, second, trace, intersect. Y'all have done this before. Enter, enter, enter. And we get 14.3. 14.3. So that means if t is 14.3, t equals 0 is 1990. So if we add 14 to that, what year are we talking? 1990 plus 14? 2004. Okay, in the year 2004 is when the closing cost was predicted to be $10,000. Okay, let's keep going with these models. Look at number 3 and 4. They ask us to use a different model. They ask us to use a logarithmic model. Number 3, the table to the left gives the percent of all workers who are female during selected years from 1970 to 2006. Using a logarithmic model, use an equation for the curve of best fit, then estimate the percent of female workers in 2016. So here's something that you got to know if they ask you to use a logarithmic model. You can't put t equals 0 in, okay? It won't calculate it if you use t equals 0. So let's just say that 1970 is 70, 80, 85, 90. So 2006 would be what, 106? Okay, I'm kind of starting from 1900. That'd be 106. That's what we need to put in our table. Stats, edit. 70, 80, 85, oops, 90, and 106. And we've got 30, 35.3, 37.9, 37.2, 41.5. Okay. It asks for a logarithmic model. So we need to go stat calc. Let's look for a log. I don't see an LOG. Okay, it's not logistic. Okay, it is not logistic. It's the LN. Remember I told you that there was another log? There's the LOG and there's the LN. So this is number 9. LN regression. So here's our model. Look how it's a little bit different. So we've got population equals A is negative 81.931 plus, look at the model there, plus B 26.603 ln of, we're using T instead of X. I'm going to put a little time symbol there so that you don't think the ln is a 1. Okay, then estimate the percent of female workers in 2016. So what did we plug in for 2016? $116, thank you. 1/16. So negative 81.931 plus 26.603 times ln of 1/16. The LN button is right below the LOG button. It's right beside the number 4. So this model tells us that the population in 2016 is approximately 44.5 millions. Oh, the percent of all workers. So approximately 44.5% of workers are female in 2016. Okay, let's do another one. The table to the left shows the height in feet of a pine tree in the park when it was originally planted. It was 1 year old and had a height of 4 feet. Using a logarithmic model, write an equation for the curve of best fit and determine the age of the tree at 20 feet. So let's put the data in. Everybody needs to be putting in the data because I know it's going to happen. Somebody here in a minute when I turn you loose is going to say, I don't know how to put this in because you weren't trying to do it when everybody else was. Okay, so 1, 2, 3, 4, 5 goes in list 1. 4, 6.3, 7.9, 9.2, 10.3 goes in L2. Second mode. Go back to the home screen. Stat, over to calc. LN regression, natural log regression is number 9. So I'm going to use that H for height. So we've got 3.818 plus 3.887 ln of t. I usually write my LNs in cursive so that I know the difference between my L and my 1s. Now it says determine the age of the tree at 20 feet. So do we plug in 20 into our equation? Do we plug 20 into our equation for t? Is 20 feet a time? No, 20 feet is not a time, so that must mean that our equation is equal to 20. Now, we can do it graphically like we did just a second ago, or we can solve this by getting the natural log by itself. So I'm going to do it mathematically or algebraically because it's quicker. So 20 minus 3.818. How do we get that natural log there by itself? How do we get the natural log by itself at that point? What's being done to it right now? It's being multiplied. So what's the opposite? Divided. So we divide both sides by 3.877, so we get 4.163 is equal to the natural log of t. Now here's how you solve this. The base of the natural log is e, so we write it in the exponential form. E to the 4.163 equals t. So e is second ln to the 4.163. It's going to take a long time. 64.3 years. Okay, so it's growing pretty quick to start with, and then it kind of starts to level off, and it takes a longer time to get to 20 feet. Now you could could have done this by graphing. Let me show you that as well. So we plug 20 into y1. We plug our model into y2. We got to adjust this window because the previous window is not going to work. Okay. We'll leave the x minimum at 0 because that's age. Obviously, it can't have negative age. Okay. It goes up to 5 right now. Now, I know that the answer is 64, but let me show you. Let's leave it at 20. Okay, 20 may have been a good estimate or guess. Okay, the y's are referring to the height. So let's go with 0. And we need to know when it's 20 feet, so I'm going to give myself a buffer. I'm going to go to 25. Okay, so let's graph it. So there's my 20 feet. Here comes my logarithmic model. Okay, it hasn't quite reached it yet. We're looking for the intersection, so that means I need to increase my window. I'm a good bit away from it, so I'm going to jump up to 75 and then press graph again. Okay, now I can see where they cross right here. So second trace, intersect is number 5, enter, enter, enter. 64.3. Okay, so you got to be able to know how to find where it is on the graph to be able to do it graphically, or I showed you how to do it algebraically as well. Okay, so we'll do the